Okay, let's begin by taking a look at our metric stair-step method. You've already seen this stair-step method here, so this is how we can convert from the base unit up or down. We have another metric system handout which should be in your folder or in your spiral notebook. Let's look at the prefixes for the metric system. Pico is a small p, and it's 10 to the 12th is the power of 10. Nano is a small n, 10 to the negative 9. Micro, this is the Greek letter micro. It looks like a U with a tail, 10 to the negative 6. Milli is a small m, 10 to the negative 3. Centi, small c, 10 to the negative 2. Kilo is a k, 10 to the 3. Mega is a capital M, so it's not confused with the small m here or the meter or anything else. It is 10 to the 6, and giga is 10 to the 9th. You might be familiar with these from computing, kilo, megabyte, kilobyte, megabyte, gigabyte, terabyte, that sort of thing. Okay. Each of these, if you're doing the self-grading, is worth 1 point. So this is a total of 16 points. The next section here, 9 through 13, we're looking at converting each of these into a unit which is a number with a prefix in front of it, which is more reasonable for the size of the number. So 1,000 grams is 1 kilogram. 0.001 grams is 1 milligram. This right here, if we move our decimal point over 3, 6, 9 places, becomes 340 nanometers. This right here, 93 million miles, would become 93 megamiles. We really don't use the metric prefixes with English units, but we're practicing the prefixes, not the units. And in this case here, if we move the decimal place over 3 and then move it over another 3, we end up with 5.21 microseconds. That's the small little u with the tail, the Greek letter micro. Okay, let's look at 14 through 21. We're going to write these numbers in scientific notation. We need to move the decimal point until it's right after the first non-zero number. I'm going to mark a few of these here. So this first one, we're going to move it over 2 to the left. Now this 0 is significant, but after we move it over 2 to the left, we end up with 1.5690. Again, this is significant, times 10 to the 2, because we moved it over twice. Here we're going to move the presumed decimal point over 4 places to between the 1 and the 2. So it's 1.2 times 10 to the 4th. These zeros are not significant. Here we're going to move the decimal point over until it's just after the first non-zero number. So we moved it over 2 to the right. So the power is 10 to the negative 2. And it becomes 3.45 times 10 to the negative 2. Here we're going to move the decimal point over 4 places to just after the first non-zero number. So it becomes 8.9. And this 0 is significant. So it should be 8.90. So there should be a 0 right here times 10 to the negative 4. Number 18, we'll move the presumed decimal point 3 places to the left, so this becomes 3.5 times 10 to the 3 meters. Here we're going to move this over 3 and then another 4, 5. So we'll move it between the 6 and the 5, so we have 6.5 times 10 to the negative 5 kilograms. And note that these on this side have units, so the units are important. Here we have 16 million centimeters. So we're going to move this over 3, 6, and then 1 more to put it right after the first non-zero number. So that's 7 places. So we end up with 1.6 times 10 to the 7 centimeters. And the last one is 0.0004 and so on. So we need to move this decimal point over 3, 4 places to the right. Now, all of these numbers are significant, including the trailing 0. So we have 4.00970, right here, 4.00970 times 10 to the negative 4. We moved it over 4 places, centimeters. number 22, 1.23 times 10 to the 6th becomes 1,230,000. 2.5 times 10 to the negative 3 becomes 0.0025. 1.54 times 10 to the 4th becomes 15,400. And 5.67 times 10 to the negative 1 becomes 0.567. Let's look at 26 through 31. 6.6 divided by 3.3, if we look just at those, that's 2, or 2.0 if we want to use our significant figures rules. So we have 2.0. And then 10 to the minus 8 minus 10 to the minus 4. If we do minus 8 minus 4, we end up with a minus 4. So 2.0 times 10 to the minus 4. Here we have 7.4 divided by 3.7, so that works out to 2.0. And then if we look at our powers, 10 minus 3 is 7. So this is 2.0 times 10 to the 7th power. Next we have 2.5 divided by 7.5. Well, that's 0.33. And 8 minus 2 is 6. So we have 0.33 times 10 to the 6th. But unfortunately, this is not in correct scientific notation format. We need to move our decimal point over one place to the right to get 3.3. When we do that, we'll have to take 1 away from our power, so it becomes 3.3 times 10 to the 5. This is the correct answer in the correct scientific notation format. Now, is this number the same number? Well, of course it is. But it's not in correct scientific notation, so we need to fix that and report it here. So here we have 1.56 times 10 to the negative 7 plus 2.43 times 10 to the negative 8. The problem is that the powers of each of these two numbers is not the same. This one is negative 7 and this is negative 8, which means we cannot add them together or subtract them. So in order to fix this, what we need to do is we need to convert both of these to the same power. What we can do is we can move the decimal point one place over to the left on this number right here, and we end up with 0.243 times 10 to the negative 7. Now we can add these two numbers together. 1.56 and 0.243 add up to be 1.803. And the power, since it's the same on both, stays the same in the answer. Negative 7, negative 7, negative 7. Here, 2.5 times 3 is 7.5. And if we look at the exponent, negative 8 plus a negative 7 is a negative 13. So 7.5 times 10 to the negative 13. Here we have subtraction. This one is 2.3 times 10 to the 4th. This one is 2.0 times 10 to the 3rd. So the problem is the place values of this this is really in the thousands place, and the place value of this number is in the 10,000s place. So this is 23,000 and this is 2,000. So in order to get them in the same place value, that means we need to make these numbers be the same, 10 to the 4th and 10 to the 3rd. So we can do that by moving the decimal place over by 1 right here. When we do that, we move this over by 1. That means we have to change this number also by 1, so we'll move this up by 1. So now we have 2.3 times 10 to the 4 minus 0.2 times 10 to the 4. 2.3 minus 0.2 is 2.1 times 10 to the 4. Here we're going to work some math problems. The sun is 1.49 times 10 to the 11th meters away, and light travels at 3.00 times 10 to the 8th meters per second. So we have here a distance and we have here a speed or a velocity. So velocity, speed, is equal to distance divided by time, but they're asking how long does it take. So we need the time number here, Velocity is distance over time. This is what we're looking for. Well, in algebra we can do this little magic switcheroo, which I've shown you guys before, and we can say that time is equal to distance divided by velocity. So we can take our distance right here and substitute it in. 1.49 times 10 to the negative 11 meters. We'll divide by our velocity of 3.00 times 10 to the 8th meters per second. Notice that seconds has flipped up to the top since we're dividing it down here. When we have something that looks like meters per second, that means meters divided by seconds. So meters on the bottom divided by, flip it to the top, seconds. So meters down here cancels with meters, and it leaves us with units of seconds. 0.5 times 10 to the negative, or times 10 to the 3 seconds is the same as 5 times 10 to the 2 seconds. If I remember my math correctly, this was 4.97 times 10 to the 2, which is 497 seconds. If you want to take that further, you can divide by 60 and you get a little over 8 minutes. So it takes 8 minutes for light to reach the Earth from the sun. Just over. An electron has a mass of 9.11 times 10 to the negative 31 kilograms. What is the mass of a mole of electrons? So here we have 6.02 times 10 to the 23rd electrons. So we just have our little E negative sign. And this is kilograms per electron. So the electrons cancel and it leaves us with kilograms. 6.02 times 9.11 gives us 54.84. And if we take 23 and we add it to a negative 31, we get a negative 8 kilograms. So we end up with 54.84 times 10 to the negative 8 kilograms. Well, this is the correct number, but it's not in correct scientific notation. We need to move the decimal point over by 1, and when we do that, we get 5.484 times 10 to the negative 7 kilograms. Also, what we should do is get rid of that last significant figure, because how many significant figures do we have here and here? Well, we have 3 sig figs and 3 sig figs. So our answer should have 3 sig figs. So 5.48 times 10 to the negative 7 kilograms. Number 34, a metallic rectangular solid of 1.44 times 10 to the negative 3 kilograms has sides of the following dimensions. Determine the density of the solid using appropriate units. So density is equal to mass divided by volume. So we're going to put the mass up at the top, and we'll put the volume down at the bottom. The volume is length times width times height. So we'll put our 3 length dimensions on the bottom. So we have 1.44 times 10 to the negative 3 kilograms, and we divide by all of these. Now, normally I would not recommend multiplying all of these together and then plugging them in, but since they're easily done in your head, 4 times 1 times 5 is 20. So we have 20 times 10 to the negative 7 meters cubed. We can do this in our head, and this will help us with solving this. 1.44 divided by 20 is 0.072, and minus 3 minus a minus 7 is 4. So we can actually do this in our heads. We get 0.072 times 10 to the negative 4th kilograms per cubic meter. Then we're going to convert that into proper scientific notation by moving the decimal point over twice. So we get 7.2. Up here we've got to change this number, decrease it by 2. So 7.2 times 10 to the 2 kilograms per cubic meter. Once we get down to these small digits, we can just write them out. This is the same as 720 kilograms per meter cubed, or per cubic meter. Number 35, rank the following mass measurements from smallest to largest. The first thing we need to do is convert them all into a consistent set of units. So let's move them all to grams. 0.61 times 10 to the 3 is 610 grams. The next one is 7.2 grams. This is 20 grams. This is 0.141 grams, and this is 0.0000562 grams. So this one's clearly the smallest. This is the next. We come over here to the middle one here. This is the next. then number 4 is this one, and the largest number is this one right here. So in order of rank, they go 5, 3, 4, 2, 1. I've done another video already about the difference between fundamental and derived units. However, in fundamental, in the SI system, the units for mass are kilograms, for area, square meters or meters squared, length is meters, volume is meters cubed, speed is meters per second, and density is kilograms per cubic meter. Now, a lot of people think that this should be grams, but the answer is no. This is the base unit, but it is not the standard. The standard is sitting in Paris, and it's a block of platinum alloy, and it is a standard kilogram, which was thought to be better than using a tiny little thing with the mass of a paperclip to be our standard. So the standard is actually the kilogram, but the gram is the base unit. Okay, but this is our standard. Also, you may find a lot of people saying that the liter, L-I-T-E-R or R-E, depending on your country of origin, is the standard. But no, this right here is a decimeter cubed, meaning 10 centimeters on a side, and it is the base unit for metric volume. But when we talk about SI units, we're going to use the cubic meter for that. So metric system use liter, SI unit will use cubic meter. The difference between fundamental and derived, there are only 4 fundamental dimensions, let's say, in the universe. 2 of them are listed here. Mass, which is the amount of stuff, and length, which is one of the dimensions of something like area or volume. Those are 2. The other 2 are time, which is measured in seconds, and charge, which is measured in coulombs. We won't study that until the next semester when we talk about electricity. But we've got mass, length, time, and charge. All the rest are derived, meaning they're made of other units. So an area is made of 2 perpendicular length units, length times width. Volume is made of 3 perpendicular length units, length times width times height. Speed is a length unit divided by a time unit, so distance over time, meters per second. Density is a mass divided by a volume, so it's a fundamental unit divided by a derived unit to get another derived unit. Let's look at the appropriate metric prefixes. 100 meters is hecto, a hectometer. 10 to the 9th seconds is a nanometer. 10 to the negative 2 meters is a centimeter. 10 to the negative 6 meters is a micrometer. That's with the small little U-shaped Greek letter micro. 10 to the 6 moles is a megamole. That's a capital M right there, big capital M. And 0.1 liters is a deciliter. These prefixes have been preserved in our money system. This is 1 cent, which is 1/100th of a dollar, a penny, 1 cent. And deci, through several languages in between, has become our dime, which is 1/10th of a dollar. So a deci means 1/10, and we get our unit, or our money system dime. Centi is 1/100th, and there are 100 pennies in a dollar. So 1 cent. Okay, estimating sizes. Don't forget the units. Raisin is a mass of about 1 gram. A nickel has a mass of about 10 grams. Actually, it's about 5 grams, if I remember right. The width of a paper clip, a centimeter. 2.2 pounds is about 1 kilogram. A candy bar is about 10 centimeters. It's about 4 inches. A yard is 3 inches shorter than a meter. And a little more than half a mile is 1 kilometer. To the nearest power of 10, the width of this room, 10 meters. That's a little over 30 feet. The height of your desk, 100 centimeters. which is about a meter, which is 3 feet. The mass of your body, well, to the nearest power of 10, that'd be 100 kilograms. For me, that's 220 pounds. Now, you could go under that and say 10 kilograms, but that would only be 22 pounds. So what's closer? The length of your pencil in millimeters, 100 millimeters, 10 centimeters. Again, that's about 4 inches. But we could go either way on that, and then it would be either much too big or much too small. The length of a football field in meters is about 100 meters, which is actually a little longer than a football field. It's about a football field including the end zones. The number of students at HHS, about 1,000 to the nearest power of 10. So really we've got 2,500 students, but to the nearest power of 10, that's the thousands place. Okay, so if we went up to 10,000, we'd be way over. If we went down to 100, we'd be way under. So the nearest power of 10, that'd be 1,000. Let's take a look at our number line. We've got a metric number line right here. We're going to label each power of 10 with the appropriate prefix. Now, prefix, let's assume that we're using a base unit of meters. We don't need to use a base unit of meters. This could be liters or kilograms or seconds or anything else. But going from 10 to the negative 12, this is pico, nano, micro, milli, centi, deci, and then here's the base unit, and m for meters. Going up one, there is the dk, which is one way to do this, or capital D. D and dk are both the same thing. They both stand for deca. H is hecto, K kilo, M, capital M. So this is MM for megameters, GM for giga, and TM for tera. These guys all have to be capitalized. Okay? This guy, if you use a capital D instead of the dk, all need to be capitalized. Moving on to the next section, 80 through 85, the conversions. How many seconds in a year? So we're going to assume that a day is 365, or pardon me, a year is 365 days instead of what it actually is. But 365 days, 24 hours to a day, 60 minutes to an hour, and 60 seconds to a minute. So days cancels with days, hours with hours, minutes with minutes. It leaves us with the units of seconds. Written out SEC, although right here the abbreviation is S. 31,536,000 seconds. 28 kilometers into centimeters. Now we can do this with the stair step. We can follow our little stair step pattern, which has kilometers over here and centimeters down here. We can count up 2 to the base unit, and then 3 more to kilometers. And if we do that, we end up with moving the decimal place over 5 times. But instead, we're going to use the factor label method, which is essentially unit conversions or train tracks. We call this train, put the I in there, tracks, or dimensional analysis. This is also called dimensional analysis. Okay, or factor label method. This is because often these are conversion factors, and we're mainly looking at the labels that go into the conversion factors. So 28 kilometers is our starting point, so that goes at the top on the left-hand side. If there's only one unit, the unit is on the top. Sometimes there are 2 units, like meters per second, so we have a unit on top and a unit on bottom. But here we just have kilometers. 28 kilometers. I need to get rid of kilometers and convert something closer to the base unit. So the base unit, there are 1,000 meters in a kilometer, so 1,000 meters in a kilometer, so kilometers cancel. Now I'm going to convert meters, which is all that's left, into centimeters. So there are 100 centimeters in a meter, so now units meters cancel. It leaves us with centimeters. And I end up with 2,800,000 centimeters. Notice that the decimal point moved over 1, 2, 3, 4, 5 times. The same 5 stair steps that I would have taken if I was doing this. If I had the base unit and centimeters, I would have gone from centimeters pardon me, from up here from kilometers, I would have gone down 1, 2, 3 steps to the base unit, 4, 5 to centimeters. So 3 to the base and 2 below that is a total of 5 steps. So I moved the decimal point over 5 times. But factor label method or dimensional analysis, train tracks, this is the way to go here. 50 grams to kilograms, so I'm starting at the base unit. 1 kilogram is 1,000 grams, so I put the what I'm trying to get rid of on the bottom, grams, and 50 times 1 over 1,000 gives me 0.050 kilograms. 45 kilograms to milligrams, so I'm going to go to the base unit first. 45 kilograms, there are 1,000 base units in a kilo unit, so 1,000 grams per kilogram, so kilograms cancel. Then milligrams, there are 1,000 milligrams in a gram, so milligrams, grams cancel with grams, and that leaves me with milligrams. So I have 45 million milligrams. Meters per second to meters per hour. So I start with 450 meters over seconds, meters per second. Notice that seconds is on the bottom. So whenever we see this slash here, that means we're flipping sides of our train track. So if we're on the top, we move to the bottom, meters per second. Now I need to move, the meters is the same in the given and in the answer, so I need to convert seconds into hours. Seconds are on the bottom, so to get seconds to hours, since I don't know how many seconds there are in an hour, I'm going to convert seconds into minutes first. There are 60 seconds in a minute. Now I don't want to put minutes on top, I want to put minutes on bottom, because seconds on top means it cancels with seconds on bottom. So there are 60 minutes in an hour, so I put minutes on top so they cancel with these minutes on bottom, and it leaves me with hours on the bottom. What are my two units? Meters on top, hours on bottom, so meters per hour, 1,620,000. We multiply across the top, 450 times 60 times 60. Divide everything on the bottom, divide by 1, divide by 1. Don't really need to do that, we can skip that step. Okay, let's take a look at the next one. 3.3 kilometers per hour into meters per second. So I have two conversions, the length and the time. So I'll start with 3.3 kilometers per hour. Hours is on the bottom. First I'm going to convert the distance unit into meters. So the first thing I do is I multiply by 1,000 meters per kilometer. This lets me cancel kilometers. The two units that are left are meters per hour. So now I need to get rid of hours and convert it to seconds. Well, 1 hour is equal to 60 minutes, so if I put the hour on top, and then the hours and the hours cancel with each other, and I end up with meters per minute. But that's not really as far as I need to go. I need to keep going. So there are 60 seconds in a minute. I'm trying to get rid of minutes on the bottom, so I'll put minutes on the top. Minutes, minutes, cancel out, and it leaves me with seconds. So my units for my answer are meters. It's the only thing left on top. Per second, the only thing left on bottom. And so that's what they asked me for, and that's the answer I get. I multiply everything across the top, 3.3 times 1,000. Then I'm going to divide by 60, and then I'm also going to divide by 60 again. Okay, so multiply everything on top, divide, 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 divide on the bottom. No multiplying on the bottom. Multiply only things on top, divide, 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 divide on the bottom. Okay, this stuff is just for fun. 10 to the 1 cards is a deck of cards. 2 times 10 to the 2 with it is 2 heck with it. 2 times 10 to the 3 mockingbirds is 2 kilo mockingbird, or to kill a mockingbird, right? 10 to the negative 3 Terry is military. 10 to the 3 Manjaro is Mount Kilimanjaro. 10 to the negative 6 phone is microphone. 10 to the negative 12 booze is a peekaboo. And 10 to the negative 10 to the negative 2 mental is sentimental. Of course, in reality, that would be spelled with a C. Sentimental is spelled with an S, but senti, the prefix, is with a C. And a lot of these are, of course, not spelled the way you would normally spell them. Alright, we're going to skip these because I cannot read this. Need to scan this with a little bit darker, and then we can do this one.